intrigued me for a while now. Um, this topic is called relativity, and you've probably heard of it by now, or I don't know. You've probably heard of relativity, and, and the reason I say that is because I've known about this topic since I was 9 or 10 years old. But and I understood, even then I understood that this topic that I was watching on like a PBS Spacetime video, I still understood how unbelievably important it is to our current understanding of the universe. But for so long, I knew literally nothing about it. I knew it had something to do with the flow of time and the effects of going really, really fast or going near a really, really big object. But outside of that, I couldn't wrap my head around anything more. It was only until a little over a year ago when I opened a textbook and I learned all the mathematics behind relativity. And it was so difficult to understand. But when I say it was difficult to understand, I want to. It wasn't like I was learning calculus or anything. It wasn't look like I was learning linear algebra. It was, in fact, the math was actually comparatively simple. As far as physics goes, this math was actually pretty simple. It was actually the concept that I just couldn't get my head around it because it felt so unintuitive. Yet it showed me that while some things in this universe may be far too grand for our minds to understand, there is still the language of mathematics that can guide us while our senses are blinded. And that's what I hope to replicate to you all today. I hope to take you all on a tour of all that we've learned about relativity while showing you the beautifully simple maths behind it. And interestingly, this tour does not start with Einstein, although you may assume that. It actually starts with Newton. And this is because relativity is actually a very old concept. There is no need to actually travel really, really fast or go near a really, really big black hole to experience the effects of relativity because it is already all around us. To understand its most basic form, we first have to understand what an inertial reference frame is. But before I dive fully into the maths, I want to give you a sort of visual representation. Just close your eyes and imagine that you're inside of a train with no windows, and you board the train. You sit down, and maybe you begin to read a book. You might order a drink, and you might place the book on the table beside you. And as you do this, nothing unusual happens. This book, it doesn't slide away or anything. Your drink, it doesn't tip over. From your perspective, everything behaves exactly as it should. The point here is there is no experiment or action you can perform without looking outside that will allow you to tell whether the train is moving or not. Any reference frame where motion cannot be detected internally is called an inertial reference frame. In these frames, an observer should be able to freely explore Newton's laws of motion without hindrance. Now, if the train starts to speed up or slow down, you will certainly be able to tell that it is moving because suddenly your drink is sloshing everywhere and your head is banging against the seat in front of you. This is called a non-inertial reference frame, and I will not be talking too much about this today, but maybe a little bit towards the end. So now that we sort of know what an inertial reference frame is, we have a small problem. It's a small problem, but a problem nonetheless. Let's say we have two observers, right? One of them is stationary. We'll say that they're stationary. And another one is moving at a constant speed. Let's say they're moving 5 miles per hour. Maybe they're taking a run or something, or on their bike or whatever. The point is, both of them are moving at constant speeds, right? So they're both in inertial reference frames and free to explore the laws of Newton's laws of motion without any sort of hindrance. But since one of them is stationary and the other one is moving, they can describe the same event in totally different ways. Let's say an event occurs at a certain place and a certain time. Well, they may agree on that time, but how, like, they may disagree on the distances between between certain events. So the question is, we have these two inertial reference frames that are both correct, but are saying different things. So the question is, how do we translate between these descriptions? And this is where something called the Galilean transformation comes in. And I kind of want to draw it out for you. Okay, so let's just let's imagine we have ourselves here a simple one-dimensional number line right here, and we'll say that this point right here is the origin. So this point right here, when x is equal to 0, and we'll say that we have a train here. Here's my nice amazing drawing of a train. Got the wheels, and it's going at a certain speed v. And let's say there happens to be another train over here, and this guy is over here, like that. And we'll say that they're both observing something. They're observing this event that's occurring over here, and we'll say that it's like a bomb or something. It's a bomb. It's got the fuse going here, and it's gonna explode. And we're gonna imagine that before these two guys do their little experiment, they get together, the people inside this train, they get together and they take some stopwatches, and they make sure to start their stopwatches at the exact same time. And so that means that both of their times should be the same. However, there is one issue, however. It's that these two observers are still seeing something slightly different. So, because for instance, this guy right here, I'll call this guy T1, and I'll call this guy T2. T1 is a distance, we'll call it x, away from the bomb. And T2 is a distance x prime away from the bomb. Now the thing is, before we really do anything, we have to establish what it means for this bomb to go off. What it means is it's an event. Now, an event, well, if you were to tell someone about an event and you wanted to meet them there at the event, you would tell them it is occurring at a certain place and it is occurring at a certain time. So, in math, we denote that as, we denote that as x comma t. Of course, there's three other dimensions. There's x, y, z. But for the sake of simplicity, I'm just gonna do x and t. Now the question is, well, the thing is, we know that both their t's are the same. Let's say this guy T1, he sees the bomb go off at some time t, and this guy over here, he sees the bomb go off at some time t prime. But since they started their stopwatches at the same time, we know that t is supposed to equal to t prime. So the only issue now is that This guy right here, well, he is a distance x from the bomb, and train 2 is a distance x prime. So they're going to see a slightly different interpretation of the event, despite the fact that both of them are in inertial reference frames. So the question is, how do we translate between these two observers? Well, it's actually quite simple. Let's say we wanted to translate from the first train to the second train. We wanted to translate from this guy's perspective to this guy's perspective. Well, the difference between them is this guy sees the bomb occur at x prime from his apparent origin, which is right here, and T1 sees the bomb go off from a distance x away from his origin. So the way we can simply translate through this is, well, we see that this guy is moving at a speed v, and since we know that their times are the same, all we can do is just say that x prime is equal to x minus vt. Similarly, if we wanted to go from t2 to t1, we would just do x equals x prime plus vt prime. So you can see here, if we started at x and we subtracted by the speed at which this guy went from going here to here and the time it took, we would get x prime. Similarly over here, if you took x prime and added that speed times time, you would get x. So these two guys are sort of the fundamentals of the Galilean transformation. So this was kind of the way we sort of reconciled with these different inertial frames for a few hundred years. I think from the time when Newton published his book, which was sometime in 1600s to 1700s. So during this time, like 100, 200 years, everything was doing pretty good. But then this guy named James Clerk Maxwell came around in the mid-1800s, and he created this, well, he was known for many things, particularly for his equations, which we call Maxwell's equations. And but there was this one equation for light that he formulated around the mid-1800s, and it predicted that in the vacuum of space, light would travel at approximately 300 million meters per second. But most importantly, the equation he used had nothing to do with the speed of an observer. So here was the equation. It was, I'll write it down here. C equals 1 over square root of magnetic of here, mu naught times epsilon naught. Now these are some somewhat fancy variables. This guy right here just means the magnetic permeability of free space, and this guy just means the electric permittivity of free space, which have a bunch of implications about magnetism and electricity, but I'm not going to delve into that here. The thing that you need to know is that these two, like this equation for the speed of light, has absolutely nothing to do, it doesn't include this stuff about the Galilean transformations. So physicists were very confused because this equation was telling them that light always moves at this speed, whereas Newtonian mechanics was telling them that its speed is supposed to be relative to an observer. So a big question was raised. Light moves at this one specific speed, but relative to what? Physicists concluded that there had to be some sort of medium, which they called the luminiferous aether, and so light would travel relative to this stationary medium. However, we can see light from planets and stars that are, uh, well, at least the latter is thousands of light years away. In fact, our closest star, Alpha Centauri A, is a good 4 point something light years away. So we 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 knew that this medium had to be pretty big if we were able to see the light from all these stars and planets. So if the medium is that big, then that also means that the Earth is traveling through it. And in the same way how walking perpendicular to a really strong wind is a lot easier than walking directly into it, the observed speed of light should also move faster and slower in certain directions. And while this is like a bunch of math here, um, there was actually an extremely famous experiment conducted in, I think it was 1887. It was conducted in 1887, and it tried to test for the existence of this aether. And I'm gonna try and draw this, the experiment which they tried to conduct out right here. So this was called the Michelson-Morley experiment, conducted by a guy named Albert Michelson and his assistant Morley. And basically, it kind of looked like this. They had let's see, they had these beams. They had these like, here. They had these beams here, and let's see. So we'll say that they had these two perpendicular wooden beams here, and we'll say that light is emitted from this point. This is a mirror. This is a mirror. And this is a detector. Let's see. Let me make sure I can actually spell. So the way this worked was, light would be emitted from this source right here. I would call this the source. And there would be this mirror that cut it through the middle, and it would cause the light to refract. Some of the light would go this direction, and then some of the light would also go this way, and they would bounce off the mirrors, they would come back here, and they would go into the detector. And the detector could measure the time difference between the light pulses. And it's a pretty complicated system. I'm not going to delve into that, but basically it had something to do with measuring the crests and troughs of waves and how they aligned with each other. Okay, anyways, so back to the experiment. For the sake of this example, I'm going to say that the Earth is moving in this direction right here. So Earth moving direction. And since it's moving in this direction, well, the thing is, this light source is on Earth, so that means it's moving with the Earth. And since the aether is stationary, we can imagine that there would be, like, say, the stationary like aether here, and the Earth would be moving in, and there would be some sort of drag force. There would be some sort of drag force experienced that the Earth would experience. And so we're just going to say, even though technically, of course, the aether isn't actually moving, it's just stationary, we're going to say that this is the opposing aether medium. And so it would be expected that if the medium existed, then the light would come here
would go here, here, here. It would diffract and go along its branches. And if it went in this direction, then it would meet the drag of the aether medium. And if it went in this direction, since this was perpendicular to the Earth's motion, it wouldn't experience any of the effects of the drag force. So as a result, this light pulse that goes in this direction should get back to the detector faster than the light source that hits this mirror. So Michelson and Morley, they sort of did this test throughout the year of 1887. But every single day, strangely, the speed of light was always measured to be the same. This suggested that there was no actual medium at all. So people tried for several years to adjust the aether theory to make it work, but all of them failed. In fact, Michelson himself actually never came to terms with his experiment results, even until his death in 1931. So there's this big problem in the scientific community where there's a split between Maxwell's equations of electromagnetism and Newtonian mechanics, the former showing that the speed of light does not depend on the observer, while the latter arguing that that is impossible based on the Galilean transformation. So who wins this argument? Well, in 1905, a little-known man, working in a Swiss patent office named Albert Einstein, published a paper titled On the Electrodynamics of Moving Bodies. In this paper, he established two postulates that would change everything and create a new theory that we call today the theory of special relativity. The first postulate stated that all inertial observers are equal. Well, this is nothing new. Newtonian mechanics fully agrees with this. Observers at rest or moving at a constant velocity all have the right to claim that their frame of reference is the correct one. It is the second postulate that is really the significant piece. The second postulate is the velocity of light is independent of the state of motion of the source/observer. Just think about what that means for a moment. That means no matter how fast the source of the observer or observer is moving, both will measure the speed of light to be the same. It's as if there is a car moving 200 kilometers per hour, and I tell you to pursue the car at 100 kilometers per hour. I assume that you would observe the car going 100 kilometers per hour because 200 minus 100 is 100, but you don't. You still see it going 200 kilometers per hour. Of course, this isn't the case for cars, but even if you travel at 99% of the speed of light, you would still measure the speed of light as a stationary observer. Now, the thing is about this is it's a little bit unsatisfying, like at least for me. When I first learned about it, I thought it was not as cool because the thing about postulates is that you can't prove that a postulate is true. You just accept that it is true because it is useful for certain applications. But anyways, so Einstein he did it. He realized that Maxwell was right all along and that Newtonian mechanics would have to be thrown in the trash. But even though he made one of the greatest scientific discoveries in history, at least in my opinion, he has also unleashed a wide variety of very strange phenomena. First and foremost, the Galilean transformation is obviously not good anymore. So we need to replace it with a new transformation, and this new transformation would be called the Lorentz transformation. So, fortunately, unlike this first one where there was a nice pretty drawing and a pretty simple step to the math, this one is a little bit more complicated, but it hopefully shouldn't be too bad. So let's say, so we're going to return back to these guys right here, and we're going to derive it directly from the Galilean transformation. So here we have x prime is equal to x minus vt, and we have x is equal to x prime plus vt prime. And what we're going to do is, well, let's think about this for a second. If these two guys are both observing, if the two people in the trains, sorry, the two people in the trains are observing this pulse of light, well, they're gonna have different opinions now because one of them is moving and the other one isn't. And since both of them have the right to claim that their x's and their t's are the same, are the correct ones, then they're going to be saying, well, no, you're the one who's the incorrect one. I'm the one who's correct. So anytime that, say, T2 tells T1 a certain time, or they tell each other a certain position, they don't really agree with each other. They think they distrust, mistrust they mistrust each other's results, and so they jack it up by a factor gamma. And so now what we're gonna do is we're gonna solve for gamma. So the way we do that is we're gonna multiply these equations together. See, we have x prime is equal to gamma squared times, we're just gonna distribute these guys together to get x prime plus let's see here, v x t prime minus v x prime t minus v squared t prime. So now we're kind of at a bit of a roadblock. However, I did realize I forgot to mention something. It's that since we agree that the speed of light in a vacuum is the same for all observers, the reason we're dropping the Galilean transformation in the first place is that now we're establishing that that 1 meter may not actually be 1 meter, and 1 second may not actually be 1 second for all, at least for everyone. So the idea that distances are the same for all observers, and there's always like a universal clock that's ticking for everyone, that idea has sort of been thrown out the window, which is why the Galilean transformation doesn't work anymore. So the way we were supposed to translate between different people is now through the speed of light, because we agree now that everyone agrees on the speed of light. So we can say that, at least for train 1, x is equal to ct, and x prime is equal to ct prime. We can then say, for this guy, that 1 over c is equal to t over x, and here 1 over c is equal to t prime over x prime. So the reason we can do this is, again, because based on the second postulate, both observers will agree on c, so we can translate with c instead of using x or t. So now we're going to divide both sides by x prime to get 1 is equal to gamma squared, so 1 plus vt prime over x prime minus vt over x minus v squared t over x times t prime over x prime. That all together. So now we have some nice cancellations, because based on what we just derived over here, we can see that these two guys should just be the same thing, so they cancel out. And then we can do some nice substitutions over here. So this section over here just equals 1 over c squared. And so this can further be simplified down to gamma squared times 1 minus v squared over c squared. And then solving for gamma, we get 1 over square root 1 minus v squared over c squared. And this is what gamma is equal to. So now we can sort of plug this stuff back in, and we can plug this stuff back in, and we can now solve for time. I'm not gonna bore you guys with more math, so I'll just do it here. X prime is equal to x minus vt. I'll just write it out here, and then so this right here, this is the Lorentz transformation. And so just from this equation, you can probably already see some interesting stuff happening. First and foremost, v is the velocity of the observer, c is the speed of light. So if we, so I said before that a car doesn't experience, we don't see the same effects. Like light, if you travel 99% of the speed of light, you will still see the light going 300 million meters per second. But if you're traveling 200 kilometers per hour, the same effect that you see with light is not seen with a car. And the reason is because, notice here, right? V over c is what makes all this stuff happen. So when v is significantly smaller than c, we have, so v over c here, if say like v was very, very small and c is 300 million, then this would effectively be 0. It would almost be 0. There would still be a number, but it would be very, very close to being 0. And 1 minus 0, well, that's just 1. The square root of 1 is just 1. And what we have left is x prime is equal to x minus vt. And doesn't that look very familiar? Because that's just the Galilean transformation. Similarly, with t, we can sort of see the same effects. Right here, this whole thing turns to 1, so it's just t minus vx over c squared. And v is significantly smaller than c squared. And since you're squaring that, v times x can't possibly be larger, be close to being c squared. So this whole thing sort of just becomes 0. And then what you have left is t prime is equal to t. These two are just part of the Galilean transformation, which means that at very small speeds comparatively to the speed of light, we can just use the Galilean transformation and nothing exciting happens. But for the cases where exciting stuff does happen, I can walk you through the math, but I think it would be a little bit more exciting if I show you some pictures. This is quite a bit of math already. So yeah, all right, anyways. So there's two major things that happen as a result of the Lorentz transformation at high velocities. The first one is time dilation. Some of you may already be familiar with this one, but it goes like this. Let's say we have a clock here. I don't know. Let me draw this in. See, we have a clock here. Now, this is no ordinary clock. What this clock does is it has two mirrors, and it fires a light pulse into this mirror, which then reflects it back to this mirror. And every single time, so there's a detector over here, and every single time the light makes a round trip back to this mirror, that is counted as one tick. Meaning, if we define the distance between these two mirrors as L, then 2L over C should equal to T. Now this is the type of clock that we'll be using here. And we got our guy, let's say we have two people. We have two people here. This guy over here, he is, we'll call this guy person A. And then there's another guy, as in a train, per usual. He just seems very excited. They're kind of looking at each other. And there's some nice, very circular wheels here. We'll call this guy person B. And he's moving in this sort of this direction. Now, before this experiment, you know, these two guys, they got together and they started their clocks at the exact same time. And both of them have this this very strange clock here. And this guy, he carries his clock. He's just sort of looking down at this guy, and this guy, he's carrying his clock inside of there. But when we have a window here, right? And both of these guys can see each other's clocks. So the train goes off and it's going places. And this mirror, it's just sort of going up and down, up and down, up and down. Person A, he sees nothing wrong going on with his clock. Person B, he looks at his clock, it's going up and down, up and down, up and down. Nothing wrong seems to be happening. But then let's say person A suddenly catches a glimpse of person B's clock inside of the train. He will see something very unusual. He will see something that looks like a little bit something like this. See, now the clock, it's not really moving up and down, right? It's not moving up and down. Well, it's because it sort of has a zigzag kind of shape. And well, that makes sense because light has a finite speed. So that means this guy's, and he's moving at a certain speed v. So, you know, the light sort of, from this guy's perspective, looks like it's kind of like bending a little bit, you know. But from person A's perspective, all right, the distance between the mirrors hasn't changed because the velocity here is completely horizontal. And we can do some Pythagorean theorem, all of our triangle stuff, but at the end of the day, we can say that this distance right here is definitely longer than distance L. So now we have this new distance right here, right? From this guy's perspective, looking into the window of person B, he sees that the tick, since there's a longer distance for being traveled here, every tick takes slightly longer. It takes 2x divided by c, equal to, we'll call this one t prime. But the strangest part is person B sees nothing wrong with his clock. He sees it going up and down, up and down, up and down, perfectly fine. Everything seems to be perfectly fine. In fact, he sees his clock to be perfectly fine, right? Both of them are in inertial reference frames. So if we actually think about it, person B has equal right to claim as person A that he is the one who was stationary and it's actually person A who was moving. So from his perspective, he technically can argue that it's actually person A that is moving in this direction, course, it would be very silly for that to happen because person A is the one standing on ground. But from a physical point of view, it is logical for it's equally as logical for person A to assume that person B is moving as person B to assume that he is the one who is stationary and it is person A who is actually moving. So from person B's perspective, his clock is moving perfectly fine, but it is actually person A's clock that is moving in a zigzag pattern. So both of them will think that each other's clocks are slower and theirs are perfectly fine. And so this creates an interesting paradox. Because let's say, uh, the train turns around and they come back together. Well, the thing is, they can't both argue that their clocks are slower than each other's, because they'll look at them like that's not possible. That's a logical inconsistency. And so this is what is famously known as the twin paradox. However, it's hardly a paradox because I answered the question while explaining to you what the paradox was. Let me repeat to you what happened. Person A is stationary. Person B is traveling at a certain speed v, but person B has the right to claim, because he's an inertial reference frame, to argue that he's the one who is stationary and person A is the one who is actually moving, and therefore he can argue that person A's clock is the one that's actually moving slower. And then when he turns around and they meet their clocks they put their clocks back together, they will find that they will argue that each other's clocks are slower than each other's. Did you catch that? I said something very, very crucial that shows why this whole paradox isn't actually a paradox. It was the very key word was when person B turns around. Think about that. What does it mean to turn around? What does it mean to go in a direction and then sort of just turn around like that? What does it mean? It means you're changing direction. And changing direction implies acceleration. And when you are accelerating, that means you are no longer in a inertial reference frame. You are now in a non-inertial reference frame, which means person B no longer has the right to claim that person A is the one who is moving and he is the one who is stationary, because he's the one sort of joshing around inside of his own train. So he can't argue that anymore. So his argument about his frame of reference being valid can no longer be true. And now person A, when they put their clocks back together, person A will actually be the one who comes out to be correct, because he was the one who stayed in an inertial reference frame the entire time. Nevertheless, however, when these two guys come back, they will still they will find that person A's clock did go faster than person B's clock, even though person B never noticed anything. He saw his clock was moving perfectly fine. Now, of course, I'm talking about a clock. I'm talking about a clock with two mirrors and shining a pulse of light. So you might be asking, how does this work with an actual clock? Well, the thing is, I don't really know, because an actual clock is made up of like gears and like iron and like metal. There's no really light over right there. So we don't really know how that works. But it works here because this is a really simple example. And we know, we've tested this, that it does actually happen, because satellites, right, the things that are allowing you to watch this video, the satellites are traveling at approximately, I think it was 17,000 miles per hour, somewhere around there. And they're traveling that's great speed. In fact, their clocks, the clocks on the satellites need to be slightly uh, changed. They need to be they need to be adjusted slightly to adjust for the effects of time dilation because they're moving at that speed. And although it is a very small difference, it is enough to cause disruption if it's not accounted for. So time dilation is one of the conclusions of the Lorentz transformation. But there is another conclusion. In the same way how time is no longer fixed, lengths can also vary between observers. This brings me to the concept of length contraction. I think the best way to explain this without getting too math heavy, because I seem to have run out of space. And I think the best way to talk about this would be talk about muons. So muons are these subatomic particles that form about 15,000 meters up in the Earth's atmosphere. And they're created when cosmic rays from the sun collide with air particles. They have extremely short lives, with an average lifespan of approximately 2.2 microseconds. But since they're traveling so close to the speed of light, they can cover significant distances before decaying. Yet, even so, when you do the math, they should only be able to make it about 660 meters before they're gone and they've decayed. Yet, however, we very often detect them at the surface. So the question is, how are they traveling 15,000 meters when their lifespan only allows for an extremely small fraction of that? The answer is that because the muons are traveling so fast, they experience strong relativistic effects. From our perspective, we measure the altitude to be 15,000 meters, and since all observers agree on the speed of light, that leads us to conclude that the clocks on the muons were ticking too slow. That's time dilation. But from the muons' perspective, they live 2.2 microseconds, and they travel the full distance. So from their perspective, we measured the altitude incorrectly. It was more like 1,000 meters, and not 15,000 meters. So who was correct? Well, according to relativity, both observers are correct, assuming they're both in inertial reference frames. We think the muons' clocks slow down, while the muons think that our meter sticks are too short.
So, of course, there's a pretty significant amount of math behind this, and I only scratched the surface. But I hope this helped you guys understand this concept that took me years to fully wrap my head around. And even now, I still don't fully understand it. But otherwise, I hope you had a good time, and I'll see you guys next time.